Let's start there. So people had lots of things to say in the reflections. Thank you for doing the reflections. I appreciate it. I definitely want to get to the fundamental theorem of calculus today, but before we get there, I want to just talk about a few examples, like kind of a velocity acceleration example. Yeah, I wrote one down. This should be good. Okay, let's say we have the following. So we're given that the acceleration due to gravity of an object, I'm not going to write the due to gravity part, is negative 32 feet per second squared. And we are told that at time equal to 1 second after the object has been propelled into the air from an unknown height, after the object is propelled upward from some unknown height, that the height is, or the height of the object is, gosh, so many words. The height of the object is, what do I have down here? Let's see, 192 feet. And then at 4 seconds after, the height is 240 feet. What is the maximum height of the object? Just to add some flavor to the question. So really this question, although asking about a maximum means we're going to have to do some differentiation at some point. Really, this is a question about using antiderivatives and initial conditions to help you find the original function. So we're given the acceleration, which is the derivative of velocity, which is the derivative of position. So we are told that acceleration is a constant, which it is if you're talking about objects as falling. If other situations, you might be having acceleration be a function because they're making up some other kind of situation. But very typically, acceleration here is negative 32. I'm not going to write the units there, we're just say negative 32. And then we're going to anti-differentiate to find the velocity. So I'm just going to write velocity here. So velocity is going to be the antiderivative of acceleration, which is going to be negative 32 times t plus some constant. Usually I write plus c, but here I'm going to write plus v naught because that's the constant is the initial velocity, which we weren't told, right? Nobody told us how fast we were throwing this thing up in the air at the beginning of the situation. So we move on. So I don't know anything more I can do at the moment. So now I'm going to find the position function or the height function by anti-differentiating the velocity function. So the height, and I am thinking height here because I'm thinking about throwing this thing straight up in the air, I suppose, but you could call it position just as well. The height's going to be the antiderivative of the velocity function, which is the antiderivative of negative 32t plus the constant v naught. And we're going to anti-differentiate this in the same sort of way. The antiderivative of t to the first is t squared over 2. So we're going to get negative 32 times t squared over 2, which is going to simplify to negative 16t squared. The antiderivative of a constant is that constant multiplied by your variable. And then we're going to add on a new constant, which I'm not surprisingly going to call h naught, the height at time 0. And now our job is to, and I guess I could simplify this, right? This is negative 16t squared plus v naught t plus h naught. It's kind of gross. Yes, thank you. That H looks suspect over there. Now my job is to use the given data points, time equal to 1 second, height equal to 192 feet, and time equal to 4 seconds, and the height equal to 240 feet, to figure out what the constants V naught and H naught are. So let's do that. If I can move this piece of paper without disrupting the ever fragile document camera. I feel like I just talking about it might jinx it. Okay, so we know that h of 1 is going to equal, what did I say, 192 feet. And I'm going to actually plug in the 1 to my function here and say, oh, that's going to be negative 16 times 1 squared plus v naught times 1 plus h naught. Signed up. 192 equals negative 16 plus v naught plus h naught. And similarly, I'm going to plug in 4, and that's going to get me a height of 240 feet. And that's going to be negative 16 times 4 squared plus 4 times v naught plus h naught. And then simplifying this a little bit, 16 times 16 is 256. So I've got negative 256 plus 4 v naught plus h naught. And now you could attempt to solve for h naught and v naught in kind of whatever way you like. One easy way would be to isolate h naught in each of these and set them equal to each other, or isolate h naught one of them and plug it into the other one. But my preference here would be, since h naught specifically has the same coefficient in each equation, I'm just going to subtract these equations from each other. So I'm going to do this equation. Oh, sorry, equation, apologies. This equation minus this equation. I would probably actually subtract in the other direction, but oh well. 192 minus 40, 240 is negative 48. Negative 16 plus 256 is 240. And v naught minus 4 v naught is negative 3 v naught. And specifically here, h naught minus h naught is 0. I think that tracks. That looks all right. Then I'm going to bring everything to one side. Well, I'm going to bring the 240 over there, even though I don't love all the negatives, I'll do it. So negative 48 minus 240 is negative 288. It's equal to negative 3 times v naught. Quick question, thumbs up or thumbs down for yes or no. Is 288 divisible by 3? Thumbs up for yes, thumbs down for no. What's 2 plus 8 plus 8? 2 plus 8 is 10. 10 plus 8 is. What's 1 plus 8? Is 9 divisible by 3? So then so is 288. So fast way to check if something's divisible by 3. So then we can divide this by 3. 288 divided by 3. 3 goes into 28, 9 times. 9 times 3 is 27. Subtract. 3 goes into 18 6 times. So the initial velocity is 96 feet per second. Cool. So now we can update our model a little bit. Probably getting ahead of myself there a little bit, but fine. Yeah, let's, instead of updating the model, let's just go ahead and find h naught. So then we can plug this in for v naught here and solve for h naught. So h naught in this first equation is going to equal 192 plus 16 minus the value we just found for v naught, which was 96. So that's going to be, I think, 112. Let's see. 16 minus 96 is negative 80. 192 minus 80 is 112. So now we've fully got the antiderivative with these initial conditions. We have that our height function is equal to negative 16t squared plus v naught, which is 96 times t. I wish my t's and my pluses looked a little bit more different than each other, plus h naught, which is 112. And we also know that the velocity function, which is the derivative of that, is going to be negative 32t plus 96. Again, neither of these things were actually what the question was asking for, but they are worth looking at. And we definitely need them to answer the question. So back to the outstanding question. Oops, sorry. The outstanding question is, what is the maximum height? So to find the maximum of a function, we take its derivative, which is equal to 0. We find the critical value. We plug it back into the function to find the output. So here, I'm going to set the velocity equal to, which totally makes sense, right? If you're thinking about trying to find the max height of a ball or something thrown up in the air, it's going upwards, its velocity is positive, it tops out, and then its velocity is negative because it's changed direction, it's going downward. So the place where the velocity goes from positive to negative is going to be where the velocity is 0, where we have a horizontal tangent line, and that's where we're going to have a maximum height. So take the velocity, set it equal to 0. I would probably just say 96 equals 32t, and 96 divided by 32 is exactly 3. So when time is equal to 3 seconds, that's when we're going to achieve a maximum height. And then we're going to plug 3 back into the original function, the height function, to find that actual height. So plugging t back into the height function, we're going to say that h of 3 is equal to negative 16 times 3 squared plus 96 times 3 plus 112. Interesting thing. Yeah, interesting. Yeah, I think it's interesting. That I've noticed over the years is when you're finding the maximum of a quadratic function, a parabola, you're finding the vertex. And what always happens is this number here and this number here are always oppositely signed. And this number here is always exactly half of that number there. It's really true. Like it's not a coincidence that it happens. It's actually true for reasons like because you could factor this thing by completing the square and then finding the vertex that way, and it would exactly work out the same way. So I'm seeing here that this is going to be 16 times 9, or 4 times 4 times 3 times 3, or 4 times 3 times 4 times 3, or 12 times 12, which is 144. And 96 times 3 is going to be exactly double that. 270 plus 18 is 288 plus 112. That plus that is 144. 144 plus 112 is 256 feet high. That is the maximum height of this ball that we threw. That we only knew the acceleration and how high it was at a couple points. Cool. So really, though, this is more of an example of solving a differential equation or finding the antiderivative of the function and solving for the constants using the initial conditions. Questions about this? Okay. Sorry, I have one other one kind of in the same vein, but a little bit different. And then I think fundamental theorem of calculus. So here's another question. This one more like what someone asked me about. Yeah. We have a bacterial colony, bacterial, sure. Something's growing, a fungus, a bacteria, whatever. Bacterial colony increases. Now, be careful with the words here. At a rate of 5e to the 2t per hour. 5e to the 2t bacteria per hour. Okay, bacteria per hour. The initial, another initial condition problem. The initial number of bacterium, I don't know. Bacteria, not bacterial, this is terrible. Is 80 bacteria, exactly, yes. And we want to know what is the population 6 hours later. So this is where the words really matter. Specifically the word rate. So they're not telling us that the population of bacteria is equal to 5e to the 2t. They're telling us that it's growing at a rate of 5e to the 2t every hour. Or in other words, the rate of change of the number of bacteria is 5e to the 2t. Or in other words, the derivative of the number of bacteria is 5e to the 2t. So if b of t is equal to the number of bacteria at time t, then the derivative of that, b prime of t, or as I would rather write, db dt, is equal to the rate of change of that number, which we were told was 5e to the 2t. So what we're saying here is that db dt is equal to 5e to the 2t. And we're being asked to find the number of bacteria at 6 hours later. So we're being asked to find what b of 6 is equal to. You could view this as a differential equation. You could view it as a pure time differential equation. We're going to solve it by just anti-differentiating and then finding some constants. So if you really like, and I guess I could, yeah. You might view this as a separation of variables problem, which I don't know if people have talked about or not, but essentially you can separate the b's from the t's by multiplying, really it's not a fraction, but whatever, both sides by dt. So we have db equal to 5e to the 2t dt. And then we're going to anti-differentiate both sides. The antiderivative of 1 times db, I didn't write the 1, but it's there. The antiderivative of 1d, that variable, is just that variable. What about over here? Well, this is a great moment to talk about u substitution a little bit. And some people are kind of getting into that already. Some people aren't. But here's how you would approach a problem like, yeah, do I really want to? Yeah. So here's how you'd integrate something like, or anti-differentiate something like e to the 2t. I personally would just say, well, I'm pretty sure the antiderivative is something like e to the 2t. But if I took the derivative of e to the 2t, I wouldn't get e to the 2t. I'd almost get it. I'd get e to the 2t times 2. Right? The antiderivative is not quite e to the 2t, because if I differentiate that, I'm going to get 2 times that. So I need a 1/2 out here to compensate for the 2 that we would multiply by if we took the derivative. And that checks out. The derivative of 1/2 times e to the 2t is 1/2 times the derivative of e to the 2t, which is e to the 2t times 2. And I know I said u substitution and I didn't do it at all. So let's talk about how you would do this using a u substitution. And again, I know this is, people kind of introduce this kind of too soon, I think, but we'll go there for a minute and we'll come back. So you can also do this by doing the following kind of thing. You can say, okay, I'm trying to anti-differentiate this. And we're essentially going to replace something with the variable u. U, usually, it's the thing that's inside the argument of another function. Like if you have the square root of some stuff, the stuff is a good choice for you. Or if you have e to the stuff is a good choice for you. If you have cosine or sine or any trig function of some stuff, and you're trying a u substitution, that's often a good place to start as a choice for you. So I'm going to choose u equal to 2t. When you think of doing a u substitution, you should think of this as a translation problem. You're translating from one language to another language. I usually think of from English to Spanish. I do not speak any other languages well at all, but I think of going from English to Spanish. You don't want to be speaking Spanish with your math. You don't want English and Spanish. You want one or the other, not both. You don't want u or and t. You want just t's or just u's, not both. Specifically, the dt has to get transformed into du. That is the most important thing you're going to do when you do a u substitution. Is the first thing you should do when you do a u substitution. So I'm going to take the derivative here and say that the derivative of u, and I do recommend using that notation, the Leibniz notation, I think it's called, du dt is equal to the derivative of 2t, which is just 2. And then we're going to isolate dt so we can replace it with something in terms of du. That's going to involve, people often skip this step and just say du is equal to the derivative times dt. And then to isolate dt, I'm going to divide both sides by 2 or multiply both sides by 1/2. So that 1/2 du equals dt. So then in my translation process here, I'm first going to replace dt with 1/2 du, and then, and only then, am I going to worry about the rest. So then I'm going to say, okay, my e to the 2t, that 2t gets to become u because I said it was, so I get e to the u. If you like, and we often do, you can pull out the constant multiple in front and say it's 1/2 the integral of e to the u du. And then the antiderivative of e to the u is just e to the u. So we do actually have to anti-differentiate it, which feels like we're not doing a thing in this example because the antiderivative e to the u is itself. We get 1/2 e to the u plus c. And then finally, you have to, if it's an indefinite integral or just an antiderivative, right, there aren't any limits of integration, we always need to end up with the same variable we started with. So we have to plug back in what u is equal to in terms of either x or t or whatever letter you're using and get that this is equal to 1/2 e to the u is 2t plus c. Just like it was up here. Okay. Back to the problem we were doing. that means that B is going to equal 5 times 1/2 times e to the 2t plus some constant. Sorry, I'm kind of trying to make sure everything can be seen at once here. Okay, we're not quite done yet. We still have a couple things to do. So then we're going to still find out what the constant is. And then after we find out the constant, then we're going to plug in t equals 6 to find out the answer to the question, how many bacteria are there 6 hours later? So not too bad. So let's see here. What's the best way to do this? I'm just going to cover this up here for a second. So we're going to say that, back to the problem. We have b of t equal to 5 halves e to the 2t plus c. We know that b of 0 is equal to 80. So we have 80 equal to 5 halves e to the 0 plus c. E to the 0 is 1. So c is going to equal 80 minus 5 halves. Let's just use a decimal. That's 80 minus 2.5. So c is going to be 77.5. So then we have the full model. The number of bacteria at time t is equal to 5 halves e to the 2t plus 77.5. And then we can plug in t equal to 6, find how many bacteria there are going to be. So we're going to get 5 halves e to the 2 times 6 plus 77.5. That's how many bacteria there are after 6 hours. Yes, you could get a decimal approximation by using a calculator, and you should if you're asked to. But that's right. I mean, you could do that. I don't think we need to do that. All right. As always, you're always welcome to ask questions, clarification, or other purposes. And sorry. I've said many things in a short amount of time. Okay. I would like to show one more example of U substitution, just because I think it's odd. So I will say, as we move on and on and on, it's kind of going to be, or shouldn't it being, your favorite method of anti-differentiation, because other than just being able to do it nicely, because it's going to come up so often. So yeah. Sorry, I'm just kind of trying to think if I really want to do that. Sure, let's look at one more. So let's look at something like, we have that the rate of change of something is dm dt equal to, I don't want to do another e to the something because we already know how it's going to go. Let's say it's 100 times, sure, secant squared of 17t. And I want to find the original function t. So I'm going to anti-differentiate. And again, we can bring things to the other side. We can write this as dm equal 100 secant squared 17t dt. But really, if you just have a derivative equal to a function of that variable, the function we're looking for is the antiderivative of that thing. So we're looking for m of t equal to the antiderivative of 100 secant squared of 17t dt. And if you were to differentiate this, take the derivative of it. I know that's not what we're being asked to do, but if we were to take the derivative, eventually at the end of the process, you end up multiplying by 17, because the chain rule will tell you to multiply by the derivative of the inside, and the derivative of 17t is just 17. So I already know that I'm going to end up dividing by 17 at the end of the day here. My answer should be some antiderivative divided by 17. The reason I keep saying this is because I want you to be able to do this without doing a U substitution. I want you to be able to anti-differentiate this thing without showing any work, really, because these ones are going to be prolific. They're going to be everywhere, whatever the word is for that. They're going to be lots of places. Prolific, yeah, maybe. Anyway, you're going to see a lot of antiderivatives like this, where the argument of the function is just a multiple of t or a multiple of x, and instead of writing out the whole U substitution, like u equal to 17t, du dt equal to 17, du equal to 17 dt, dt equal to 1/17. Oh, look, I'm going to divide by 17, du. You can skip all that. Or not, if you don't want to. But rewriting it, I'm going to put the 100 out in front. I'm going to change the dt first, right? Always, always dealing with the differential before anything else when you do a u substitution. I can't say it enough or emphatically enough. This gets dealt with first. This is the most important part of your antiderivative integral thing. So dt is equal to 1/17 du. And then 100 secant squared of 17t is 100 secant squared of u. I would personally choose to rewrite it again as 100 over 17 times the antiderivative of secant squared of u, du. And then we definitely know a function whose derivative is secant squared of u. It's definitely good old tangent of u plus c. And then we change back to the original variable, which was t. So we replace u with 17t, and we get that m of t is equal to 100 over 17 times tangent of 17t plus c. No initial condition was given, so there's no way to solve for the constant c. We're just writing the most general antiderivative here. Notice, like I said was going to happen, our answer, we ended up dividing by 17. Because if you were to take the derivative of this function, you would have to multiply by 17 because of the chain rule. Okay. Let's slide into the fundamental theorem of calculus. Oh my gosh, this, I want to move that, but I don't want to mess with it. So the fundamental theorem of calculus, part 1. How do I want? Sure. So the big idea, which is kind of something I've been saying every time, is that the whole point of the fundamental theorem of calculus is that the derivative and the antiderivative undo each other. That's the whole point, is that if you do an antiderivative and then do a derivative, you're going to end up back where you started. And the way we write this is that we say that the derivative of the antiderivative from a to x of some function f of t dt is going to equal, well, if you do the antiderivative, you get something. If you do the derivative of that, you're going to get back to where you started, which is the function inside the integral. It's going to be f of x. Now, that might not be the best way of just saying it right off the bat, but that is how you write the fundamental theorem of calculus part 1. But let's do an example, because that's where we're actually going to learn things. So let's say I want to find the derivative of the integral from 2 to x of something reasonable like t cubed. Yeah, let's make it even easier. 4t cubed. 4, yeah, sure. So normally, the way someone wants you to do a problem like this, if they're giving you a problem like this, is just to say that the answer is 4x cubed. Because that's what the fundamental theorem of calculus tells you can do. It says if you're going to take the derivative of the antiderivative of a function of t, it's the same function, but of x instead of t. But we're going to do it the long way so that we can see why that's true. So now I'll point out here, and this is where things feel kind of like you're maybe doing a little bit of hand waviness, but not really, is we're going to use the second part of the fundamental theorem of calculus to show the first part works. We're going to use the evaluation theorem, which we've already been using because we have, where we're going to anti-differentiate that function and then plug in the inputs. So we're going to say that this is the derivative of the antiderivative of 4t cubed, which is just beautiful t to the 4th, evaluated from 2 to x. We always plug in the top limit first, subtract, plug in the bottom limit second. Always top minus bottom, always top minus bottom. So that's going to be the derivative of, plug in the top, you get x to the 4th, plug in the bottom, you get 2 to the 4th. We take the derivative, and the derivative of x to the 4th is 4x cubed. The derivative of 2 to the 4th is not 4 times 2 cubed. It's 0 because 2 to the 4th is 16, which is always 16, and that's a constant, and the derivative constants are 0. So look, we exactly got what we thought we were going to get. We started with the function 4t cubed. We anti-differentiated it. We plugged in x instead of t. We took the derivative and we got exactly back to where we started, except we're using a different variable. But that's the whole point, is that the derivative of the antiderivative gets you back where you started. And so then people like to start asking kind of heinous questions like, what's the derivative of the antiderivative from 3 to x of e to the negative t squared dt? And you might say, James, that doesn't look that bad. And you're like, okay, it doesn't look that bad, but it's really actually that bad because you cannot do this the long way. E to the negative t squared is famously a function that cannot be antidifferentiated. I'm gonna say it again. E to the negative t squared does not have a nice antiderivative. You know what the antiderivative of e to the t squared is, or e to the negative t squared is? It's that without the limits of integration. That's all you can do. There's no nice elementary functions, what we say, that is an expression for the antiderivative of e to the negative t squared. Such is life. So that means you couldn't do it this long way. You just have to be like, well, I believe in the fundamental theorem of calculus that the derivative of whatever the antiderivative would be is going to end up back where I started. So here I'm going to end up getting e to the negative x squared. That's it. That's all they want us. That is the expected work shown for a question like this. Is I said find the derivative of the antiderivative of the thing. I did it. I used the fundamental theorem of calculus part 1. Great. Thank you so much. Perfect question. So what if we did change the direction or the order of the limits of integration? So if we wanted to find, say the derivative of the integral or antiderivative from x to 5 of, sure, cosine of 3t dt. Well, let's do it the long way. So normally, if the x was on top and the 5 was on the bottom, we would expect the answer to be cosine of 3x, right? If the question was the derivative of the antiderivative from 5 to x of cosine of 3t, we would expect the answer to be cosine of 3x. So let's see how our answer is going to be different. I imagine many of you know what the difference is going to be already, but let's still see it so we can see it. So we're going to do the derivative. So the antiderivative of cosine of 3t, we all know we're going to be dividing by what number? On your fingers. Show me what number I'm talking about. Yes. Yes, that many, exactly. You can do this, which is like, remember, do you guys see, what's the movie where they're like, this gave them away? It was Inglourious Bastards, right? Where the guy's like 3 as an American, not 3 as a German. You haven't, it's a violent movie, but it's an enjoyable movie nonetheless. So here we're going to get 1 over 3 times sine of 3t. That is the antiderivative of cosine of 3t. And now we're going to plug in top first, bottom second. So it's going to be the derivative of 1/3 sine of 3 times 5 minus 1/3 sine of 3 times x. Take the derivative. The derivative of sine of 15 is 0. I don't know what sine of 15 is, but I know it never changes because there's no variables there. So I'm going to get 0 minus 1/3 times the derivative of sine of 3x is cosine of the stuff times the derivative of the stuff, which exactly ends up being negative cosine of 3x. So to answer your question in the longest way possible, if the x is on the bottom instead of the top, it ends up negating your answer. And really, you could do this by just knowing that when you change the order of integration, it changes the sign of your integral. So we also could have done this by saying, yeah, we know that the derivative of the integral from x to 5 of cosine of 3t dt is going to equal the negative, let's write the derivative first, James, the derivative of the negative of the integral from 5 to x of cosine of 3t dt. So then we could ask similar questions for much worse looking things. For example, someone could say, what's the derivative of the integral from x to 7 of something like cosine squared of t over 1 plus t to the 5th power dt? Really, and this plan is not my favorite. Actually, it is, but not for writing in front of people. This function is probably not antidifferentiable. a lot of examples in this genre of questions where they're finding the derivative, the antiderivative, they're going to throw just stupid things into the integrand here and be like, it doesn't matter what it is, because you don't have to be able to anti-differentiate it. So we know that it's going to be negative cosine squared of x over 1 plus x to the fifth. End the story. If you really want to, you can show the intermediate step and write this as the derivative of the negative of the antiderivative from 7 to x of cosine squared of t over 1 plus t to the fifth, but that is, in my opinion, unnecessary. So that begs the question, what if it's not just x? What if it's more complicated than x? Like x cubed or the natural log of x or something else? Well, we have an answer to that question as well. So let's say we want to find, sure, what do I want to pick here? Don't want to make it too terrible, but also not interesting. Let's say we want to find the derivative of the antiderivative from 3 to x cubed of what function shall we anti-differentiate? Sure, let's make it exciting. Secant of t times tangent of t dt. And we're going to do this the long way first, because we haven't talked about how to do it the short way. So we're going to anti-differentiate the integrand. When I say integrand, just make sure when I say integrand, it's just the stuff we're integrating, right? Secant of t, tangent of t is the integrand of this integral. So we're going to have the derivative of the antiderivative of secant of t times tangent of t is secant of t from 3 to x cubed. All right, the derivative of secant of t is secant of t tangent of t. Then we plug in our limits of integration, just like every other time. Excuse me, we're going to get secant of x cubed minus secant of 3. And now we're going to take the derivative and we're going to have to use the chain rule because the argument of our secant function is more complicated than just x. Really, I should say you can think of using the chain rule every time, whether it's x or not. At the end of the day, if your insides are x, you're going to multiply by the derivative of x, which is 1. You could always be imagining you're applying the chain rule when you're differentiating. But we're not doing that here. Well, we are, but our insides are more complicated. They're x cubed. So we're going to get the derivative secant of some stuff, which is secant of the stuff times tangent of the stuff times the derivative of that stuff, which is going to be 3x squared, minus the derivative secant of 3, which is 0. Again, secant of 3 is just a number. Or if you really wanted to do it long, you could say the derivative is secant of 3 times tangent of 3 times the derivative of 3, which is 0. But don't do that. It's way more writing than you need to do. So here our answer is secant of x cubed tangent of x cubed times 3x squared. Or the more general version of the fundamental theorem of calculus, part 1, is that the derivative of the integral from a to a function of x of f of t dt is f of, instead of f of x, it's f of g of x multiplied by the derivative of g of x. That's the more general version of the fundamental theorem of calculus, part 1. Let me give an example, and I'll try and pause. So for example, someone could ask us to find the derivative of the antiderivative from 2 to the natural log of x of e to the t over t squared plus 1 dt. Again, probably a function that can't actually be anti-differentiated. We don't have to be able to anti-differentiate it. All we're going to do here is wherever we see a t, we're going to substitute in the top and the bottom. Well, not the bottom really because it's a constant, but all the variables. So I'm going to substitute in the natural log of x for each of these t's. I'm going to say this is e to the natural log of x, more on that in a minute, over the natural log of x squared plus 1. But then what do I have to multiply by? Yeah, the derivative of the natural log of x. And I didn't mean for this to happen specifically, that it's going to kind of cancel out nicely here, but we should simplify. Oh, and I should say, right, minus 0 because the 2 doesn't do anything. But if you simplify this, e to the natural log of x is just x. So you get x over the natural log of x squared plus 1 times x. And then I guess those x's would cancel. So our final simplified answer would be 1 over the natural log of x squared plus 1. It's kind of cool. It simplifies like that, but not important really. I would probably encourage you to leave the answer like this just because it's evocative of what's happening, right? We know that, oh yeah, we're plugging in the function natural log of x, and then we are multiplying the whole thing by the derivative of that. Why don't you all try this? The derivative of the integral from e to the x to sine of x, ooh, I'm throwing something new at you, of t cubed over t plus 1. Try that. I know it's slightly different, but I bet you can figure out what you're supposed to do here. So before we say what the answer to that one is, let's look at a simpler example, one that we can actually do the long way. So if I wanted to find the derivative of the integral from x squared to x to the fourth of cosine of t, we can do this the long way by anti-differentiating the function. Antiderivative of cosine of t is sine of t, plugging in the limits of integration. So we're going to get the derivative of sine of x to the fourth minus sine of x squared, and then taking the derivative and getting cosine of x to the fourth times 4x cubed minus cosine of x squared times 2x. And that's it. Or in other words, it's your function evaluated at the top thing times the derivative of the top thing minus your function evaluated at the bottom thing times the derivative of the bottom thing. Essentially doing the normal rules for evaluating an integral along with the quote unquote chain rule version of the fundamental theorem of calculus. Because that's what that previous rule I wrote really was, sorry, it disappeared from my, it was somewhere here just a minute ago. Where'd you go? I've got my notes all out of order, which I hate, but it happens all the time. There it is right there. There's your previous, this is the chain rule version of the fundamental theorem of calculus. Yeah, okay, I'll deal with that in a minute. So back to this problem here, the way you would do this, doing the appropriate amount of not very much work is plug in sine of x, get sine of x cubed over sine of x plus 1. Yes, it's totally fine and appropriate to write sine cubed of x times the derivative of sine, which is cosine of x, minus, then we plug in e to the x and get e to the x cubed over e to the x plus 1 times the derivative of e to the x, which is e to the x. Yeah, you can simplify that a little bit, but I wouldn't bother. All right, it's almost 1:59. I probably shouldn't try to squeeze in another example. So